Hello and welcome back to Introduction to Human-Robot Interaction. This is week 3, lecture on evaluating human-robot interaction. The objectives for this week's lecture include stating the goal of HRI, summarizing the 3 perspectives of human-robot interaction, explaining how to categorize HRI metrics, summarizing the 7 stages of human-computer interaction, explaining the gulfs between execution and evaluation, describe some biasing effects for human-robot interaction effectiveness, discuss the metrics for various mobile robot tasks, and defining robot attention, demand, fan-out, interaction effort, neglect, and tolerance. The goal of human-robot interaction is to design systems that create teams of humans and robots that are efficient and effective and take advantage of the skills of each team member. Social interaction includes the visceral factors such as immediate and automatic human response and social mechanics such as behavioral during use, or social structures such as reflective impact after interaction. So if you want to have effective human-robot interaction, you want to be able to mimic some of these same qualities for interaction between a human and a robot as you would between two humans. So for example, a person's experience of interacting with a robot is influenced by many real-world social and physical factors where the robot itself plays an active role similar to that of a living entity. So what we see in this diagram here is there's going to be some physical context as well as some cultural context that the robot may not be able to pick up on as a human would, such as the human will have thoughts and feelings, social structures, etc. So when a human and a robot have to interact, it has to be about more than just the mechanics of the robot, but how can you simulate some of these qualities for the human so that it feels like efficient and effective dialogue or interaction or conversation between the two. So here is an example of an interaction experience. So here's an example of an interaction experience map where, once again, you have to look at the 3 things such as visceral factors, such as social mechanics and social structures. Like from the human's point of view, how would they perceive that a person would possibly perceive or experience this interaction? Or would a person behave? How would they behave in the same situation? Is it similar or different from how a robot would behave? Whereas a robot-centered view would be completely based upon how the robot's been designed, the visual characteristics that may affect this interaction experience. So it's mutually shaped by 2 active agents, including the human and the robot, and expectations of what they would expect to see, which may be different for the human versus the robot. So some of the metrics by which we measure human-robot interaction, it could be partitioned into interactions based upon the task, as well as interactions based upon the system. So you may want to analyze the HRI metrics in terms of 3 things: the human, the robot, and the system. So first, let's look at a task-oriented system. So here we have some mobile robots. And so from their orientation, the things that are important to the robot are the navigation. How is it moving up or down the curb? What kind of sensing is needed? What kind of perception? How are you managing this team of robots? Is there any manipulation or is there any social interaction? So those would be the metrics from a task-oriented mobile robot interaction and what you expect to see. Another example of biasing effects for human HR effectiveness would be to think about this image from the Terminator, where Sarah Connor has been told that a robot is coming back from the future in order to kill her to keep her from giving birth to John Connor. Well, if she has any kind of vision for what she expects a robot to look like, then when Arnold Schwarzenegger shows up, she may unlikely be recognizing him as the robot coming to kill her, whereas maybe a little box like this is what she is more likely to expect a robot to look like. And so she may see that as a danger. So once again, the biasing effects of HRI may be based upon how a human expects a robot to look and communicate with them, how they expect a robot to respond, and how the user is expecting the robot to interact with it, or even how the robot is expecting the user to look and engage with it. So other metrics based upon mobile robots may be navigation metrics, such as how much or what % of the task has been completed, how much area was actually covered, did the robot have to deviate from the planned route, how many obstacles were encountered and avoided, how long did it take to complete the task, how long was the operator required to engage with the robot to complete the task. If the robot got stuck on any obstacles, how does it overcome those? Obviously, this one is very unique to a mobile robot in navigation, but you would come up with similar metrics based upon whatever your robot is and how it has to complete some task or mission. Other metrics could be based upon perception. Remember, perception is when a robot takes sensor data and then uses that to come up with some kind of world model or representation. So passive examples could be identification of something in the environment, a judgment of the extent or the large or small value of that thing, like is this red ball bigger or smaller than the robot's hand, or judgment of motion. Is the red ball moving? Is it moving towards the robot's head? Is it going to hit the robot, etc.? More active perception metrics could be how long does it take to confirm and identify that it really was a red ball? Was there a way to improve upon that identification? How correct was it? How much effort did the robot have to expend in order to identify that red ball? And were there identification errors, such did it recognize it was a red ball, or did it think it was a red apple? Or did it recognize it was a ball, but it thought it was an orange ball, etc.? Management metrics may be based upon the human having to manage a robot team. Fan out would be how many robots can be effectively controlled by a human before the human can no longer do a good job at managing them. Intervention response time, how much physical and cognitive ability does the human have to expend in order to intervene when this team of robots is not working correctly? Also, level of autonomy discrepancies. Did the human think that this team was more autonomous to do something than it really could do? And did the human have to step in? Or is the human doing too much where the robots were autonomous enough to complete some things? An example of manipulation metrics could be mobile robots having to move something, or a robot arm having to move something. Did the robot think it made contact to pick something up, but it actually did not? What is the mental computation that the robots have to expend in order to manipulate something? Or how much did the operator or the user have to mentally expend in order to direct a robot team or a physical robot in order to manipulate something? Social metrics, which may be the one we want to focus on the most, thinking about our Blossom robots. What are the interaction characteristics that you're going to design for your robot? How persuasive is the robot at interacting with the human? Does the human appear to trust the robot? Is the human actively engaged socially with the robot? Is there any compliance if the robot asks the human to do something? Once again, thinking about some of those social characteristics we talked about before in terms of what the human is expecting, visceral factors to receive from the robot, etc. So some of these common metrics for measuring how impactful and correctly or effective your human-robot interaction is. They could be quantitative performance, how fast, how quickly, how slow, subjective ratings, how does the human feel about the interaction, mixed initiative use, if there's some combination between quantitative and qualitative, the operator performance, if they have to operate the robot, were they situationally aware of what was going on as they directed it remotely? Do they have a good mental model of what the robot should be doing and how it has to interact with the human? How much workload did the human have to expend in order to remotely control the robot when interacting with the human? Then from the robot's performance, how much is it aware of? Like, is it aware that it has a gripper, or that it is failing, or that it's not answering the questions, or that the battery is dying, etc., that it doesn't understand? Is it aware that a human has approached? What does it know about the human? Does it know the human's name? Does it recognize the facial characteristics? And how much autonomy does the robot have? And is it able to do the things that it should be able to do fully autonomous? Does it know when it needs intervention and it's not able to do them? So one way to measure robot attention demand is to increase the leverage that a robot offers to a human-robot team. So you want the robot to be able to do more so that the human does not have to do as much. So this could be the robot's interaction effort divided by interaction effort plus neglect time. So if you can make the interaction effort greater, then that is more robot attention demand, which you would want to happen in a human-robot team. It's not very much of a human-robot team if that number is very small, because as it gets smaller, you're moving more and more into teleoperation, where the interaction effort of the robot is not very high. You want there to be more teamwork so the robot is able to give more effort. So once again, we talked a little bit about fan out earlier, which is now where you leverage the human and how much the human is able to do, such as how many robots they're able to operate simultaneously, knowing that if this number becomes too high, then the human could suffer from physical or cognitive fatigue or constraints. So there is a fan out limit. And so what happens is you're going to have task saturation, you're going to have human memory issues, and you're going to have more mistakes. And this value is actually the reciprocal of the robot attention demand. And that makes sense. The human has to do more. That means the robot is doing less. So then you would say that that is an example of the interaction effort plus the neglect time divided by the interaction effort. And one more formula would be the human robot team can be improved by either increasing the robot's neglect tolerance, or the things the robot can do fully autonomous without the human engaging, or by reducing the interaction effort. So that would now be equal to the neglect time divided by fan out minus 1. So what are our 7 stages of interaction? It's a formulation of the goal. What do you want to accomplish, which the human will have to do? Intention to satisfy the goal, specification of the action, execution of the action, that's by the robot, perception of the system state from the robot and human's perspective, and interpretation of the system state by the human and the robot, and then evaluation of the outcome. And this is obviously iterative. So you come up with your goal, you look at the intentions for satisfying the goal, then you execute the actions on the robot to do that. Perception is now where the robot uses sensors to detect the environment to evaluate how well that was achieved. And if this is not 100% or satisfactorily achieved, it then has to go back through those 7 stages of interaction. So here are some issues when you are relating that HCI model to HRI, or human-robot interaction. There is a gulf of execution, which means there may be a mismatch between the user's intentions and the allowable actions in the system. Thinking about what this looks like in the context of a computer versus a robot. Or gulf of evaluation would be a mismatch between the system's representation of the environment or the world and the user's expectation. So let's say the robot has now achieved its goal, or it thinks it has finished a task. It represents this to the user, but the user says, no, that's not what I asked you to do. You really did not achieve the mission like you thought you did. So this one on the left is the user is asking the robot to do something to execute a mission or task that it is not capable of doing. So what are these 4 critical errors in HCI? Once again, gulf of execution. User can form an inadequate goal. It may not know how to specify a particular action to the robot, or it may not be able to locate an interaction object because the robot just simply cannot do those actions. Or that gulf of evaluation, which means you get inappropriate or misleading feedback from the system, in this case, our robot, which may lead the user to incorrectly interpret the system, the status or the state, or think the mission or task has been achieved when it really has not. So here are some examples of supervisory functions for semi-autonomous mobile robots, meaning where the robot can do some things independently, some it cannot, where you want to plan what tasks to do and how to do it. You want to teach or program the computer or robot to do that thing. And then you want to monitor those automatic actions to detect failures and whether it was able to achieve them. Since you are supervising the robot, you want to be able to intervene to specify a new goal in the event of trouble, or take over control once the goal has been reached, or take over if the robot's in trouble and not able to extract itself. This would still be true even if you're not working with a mobile robot. And obviously, ideally would be some type of machine learning where not only the human, but the robot is able to learn from experience and mistakes to improve if they have to execute that mission or task again. So now looking at the HRI model in terms of the supervisor role, what you will see is it monitors and controls the overall situation. It can specify an action or modify the plans. The main loop is perception and evaluation from the supervisor's perspective, and the actions may be generated by the robot software, and the supervisor only steps in if the robot gets in trouble. How does this differ for operator role? For the operator role, you may have to modify the software models when the robot's behavior is not acceptable. It may have to deal on the action levels mainly because it is an operator, and it may determine if actions are being carried out correctly and in accordance with the long-term goal. And notice how this changes where the loop is for an operator. And here's the HRI model for the mechanic role. And notice that the mechanic deals with physical interventions in the system. So some of those behavior changes may be done in the software. So there has to be observations of hardware and software to ensure that the behavior is now correct. So it's not necessarily iterative, but on the left, the mechanic may look at software, intentions, actions, perception, evaluation, but then it may also look at those same things from the context of the hardware. So compare this to what we had before, where for all of the other roles that we have discussed so far, it was not separated by software and hardware, but more about what the human does in terms of evaluation, perception, or action. So the next one is a peer role. And for a peer role, team members talk to each other in terms of higher level intentions. So that's where the robot is seen as a peer. And so now the two of them together may be able to talk at a higher level from evaluation to goals, where it's able to provide direct observation or perceptual input for the robot system in order to help with evaluation of whether the goals or task has been achieved. And then we have the bystander role. The bystander role is now a subset of the other interactions with the robot that is appropriate for a bystander. Remember, a bystander may not have full understanding of the robot's goals or intention. So it may not have any interaction at the role of goal or intention, but it may be able to directly observe actions and then using perception or evaluation. And I give my favorite example for this. This could be the delivery robot, where a bystander then sees the action, such as the robot should probably be moving forward right now and not being stuck in a corner or on a curb cut. And so it may step in to help. So it can give feedback only by what it directly observes, not having a full understanding of the goal or intentions, but it maybe can infer that from the robot's actions. So in order to evaluate human-robot interaction, and this is what you're going to do for your final project, you're going to design some interaction on your robot to interact with a human, design a study for that. And, as part of your study, you're going to make a questionnaire, conduct the study, which is what we would do in the Commons on the last day of class, and then analyze the data and results from that interaction in order to evaluate how well did it meet your goals for human-robot interaction. So evaluation methods, once again, could include task completion and efficiency. Are you going to have the human interact with your Blossom robot to complete some simple task? Maybe playing a game of hangman or tic-tac-toe or something like that. Was there any emotion and affective computing? Was the robot supposed to detect whether the human was angry, happy, or sad? Or was the human supposed to look at actions on the robot to determine if the robot is showing any emotion like happy, sad, angry? And situated personal experience. How was the human's personal experience in that situation as they were interacting with the robot? Was it satisfying? Was it frustrating? Was it exhausting? So that concludes our week 3 lecture, and make sure you come back for more.